we're super fast at doing, like recognizing faces. We do that immediately. So we see those two creepy guys, hovering ominously over those bottle caps there. We see this rather happy or sad-looking potato on its way to being cooked, or this super thrilled chair in the snow. So most of us just spot those faces immediately. It's part of our nature. We just do that and see it. This, by the way, is really hard for a computer to do, but complexity is really easy for a computer to do. A computer can do any size of Excel sheet or database or whatever without complaint. It just does it. It doesn't care. But it's really hard for us. So we don't like complexity. We're not very good at it. But as a species, we're kind of smart anyway. I mean, we've come up with all those great things that we've done. How do we do that if everything is so complex and we don't like it? So yeah, we have a weapon, and that is concepts, or ideas, or abstractions. This is a shared idea amongst a group of people that we can give it a name, and it hides all this complexity. All this really hard stuff with complexity behind a simple concept that we can talk about and reason about and share and be really efficient around. So just take one example there. The telephone. The telephone, phone, far away, sound. We have sound here, comes out far away. As a concept, that's pretty simple. But underneath, it's this huge mess of complexity. Even in the early days, there were those long wires, those patch bays with people sitting and patching calls through, repair people out, installation people, all sorts of complexity. But hiding beneath this pretty simple concept of a telephone. So this concept has evolved, by the way. Now we're talking about maybe not calling it a telephone, more likely to call it a phone. And it's arguably even more complex. But we have it in our hands, in our pockets, every day, all the time. We think of it as a phone. It's pretty simple. We teach our kids, this is a phone. You can do pretty much anything with it. And everyone really accepts that simple concept for a super complex thing underneath. Another example, kind of related, is the internet. The internet as a concept has evolved throughout it's been around for some 50 years or so, and it's really evolved throughout those years. And so that means that we have different perspectives on this. And if you're kind of growing up as a teenager today, you might see the internet as, it's like a collection of those apps that you use. You see your friends over Snapchat, you're watching your funny memes and videos over TikTok and so forth. And that's kind of the internet. So if the internet is down, you can't use your apps. That's kind of the concept of the internet. So there are various other ways of seeing this. You can see it as a collection of companies or a collection of large service providers whose services we enjoy using. This is the internet. It's kind of like Google or Facebook or Netflix. And it wasn't always like this. It started out as something very different. It started very technical in the 60s and 70s. And once we got to the 90s, we started to see this sort of coming into the mainstream, but not quite there. And one of the early attempts is trying to make a concept out of the internet was this famous idea. This was actually pushed by Bill Gates in the early 90s, of the internet as an information superhighway, which kind of makes sense. I mean, it's like seeing those network connections as roads, and you had cars, but it never really caught on. We don't think of it of an information superhighway today, but it was an early attempt of trying to kind of come up with a concept that we can think about. But it didn't catch on, and instead we got up in the late 90s, we sort of started to define the internet as a very technical definition, like a collection of networks, of interconnected computers. And even today, we kind of see this. If we go and look at Wikipedia, this is the Wikipedia definition of the internet. The global system of interconnected computer networks that uses the Internet Protocol suite, TCP/IP, to communicate between networks and devices. So that's a pretty complex definition. There's a lot of complexity under each and every word there. And there's a picture that's not really that helpful in terms of reducing the complexity, but it looks really complex. And for someone like me and many of us who are kind of know how the internet works, we can appreciate that picture. But for someone who doesn't know that, it really is hard to understand that Netflix or Snapchat from looking at that picture. So there are these layers of conceptualization going on. And where are we in terms of the IoT today? And what layer have we come to? And I think that we are actually around, compared to the internet, we're kind of mid-90s internet. We have those ideas of trying to conceptualize, but we don't really have a clear idea that's shared by lots of people. In fact, if you look at the Wikipedia page, it's also really technical. The Internet of Things, IoT, describes the network of physical objects, things that are embedded with sensors, software, and other technologies for the purpose of connecting and exchanging data with other devices and systems over the internet. It's really hard to kind of figure out what this means. Sure, if you know the tech, you can sort of understand it, but it's really hard to connect that into something. So I think we're kind of at the mid-90s, even though I think we're starting to see some conceptualization of the IoT. People are starting to talk about my IoTs as my IoT devices. That could be your smart home things, or it could be if you're a company that has devices out there and talk about them as your IoTs. It might be referring to your networks as your IoTs. And I think we're starting to see this kind of conceptualization coming through, but we're not quite there yet. So I thought, talking about this complexity of the IoT, I thought we'd dive into this, go into the guts of this and see, why is it so complex? What is it that makes this complex? Because that ultimately helps us answer the question why there is no one single standard for the IoT. And so I put together this list of a few reasons why the IoT is so complex. So I thought we'd kind of go through them one by one and look into this. So the first one is, there are just so many use cases, so many uses, so many places where the IoT makes sense, that each and every one have different challenges, different ways that they are created, ways that they are used, what they solve, what they do, which just kind of explodes this complexity. So I just thought I'd take a few of the examples of what we do at Thingsquare, customers that we work with in different areas, just to see kind of what we're at. And we're just one company, right? I mean, everyone has lists of this working with IoT. So, medtech. Medtech is the IoT makes a lot of sense in medtech, where you may want to check that the temperature of something is good, the viscosity of something is right, the pressure is right, that something is handled just the right way it's supposed to be handled, and so forth. So it makes sense. But in medtech, you have one set of challenges around things like approval from certain authorities. You have quite a lot of regulation there, which, because it's medicine, you have to have that. So you have to have a lot of special thoughts around that if you're in medtech. A related thing, but very different, is emergency lighting. It's also one of those life-saving things. So there's lots of regulations around it, but it's very different. The IoT makes sense because instead of having walking around checking on the batteries of each emergency light, you can do that automatically wirelessly over there, so that you can always keep it safe, and you can save on having people working around doing things that a computer could do. Again, regulation, but very different. Very large-scale installations. There is installation personnel. There are companies doing installation. There are third parties. Lots of different types of complexities arise here. Street lighting, another similar example. There are lamps, but very much larger than the other examples. Those span kilometers in each direction. Again, the IoT makes sense. It really, being able to save on power, turning things down when they're not needed, maybe turning things completely off if something happens. So, for example, we had recent example was that a street light was shining on a place where a certain animal was nesting. And because this was connected, we could actually turn off that lamp and make that animal have a better, I guess, sleep and just produce more of those animals, right? So the IoT makes sense, but very different from the others. Retail, checking on things what are people checking on in their wife's goods stores. Very different, new set of challenges, but kind of similar. You have the wireless and IoT in there. indoor lighting, water leakage detection, green rooftops, elevators. The list kind of goes on, and everyone has those lists. Everyone working with the IoT, it looks like this. There are all these use cases. So that just adds to the complexity, kind of increases this exponentially in a way. Secondly, the IoT is fundamentally about both hardware and software, because it kind of combines the power of automation that software gives us, but it has to have a hardware aspect too, because there's the physical side of it, right? So what does that mean? Well, the problem here is that hardware and software are fundamentally different in many ways. So hardware, really hard to change, takes a long time to develop, and once you're developed it and put it out, you're kind of stuck with it. But it doesn't rot. It doesn't break down naturally every day. Finally, it might break, but it's not a natural process of hardware, which it is in software. Software will rot. If you put it out there, it will eventually grow worse, so you need to have a continuous process of keeping this up to date, keeping it. It's a live thing, something living. But you can do iterative development. You can continuously add more features, do things that you couldn't do before, which you can't do in hardware. It's also pretty easy to change. You can have it out there, you can change it and update over time. Two very different types of things, hardware and software, but here we kind of have to combine them and live with that. That also increases the complexity on an organizational level. Like, how do we work with this? And going kind of deeper and deeper into the tech here, we're almost always in the realm of low-power design in terms of the hardware. We might have a battery-operated system, we could have a solar-powered system, we could have something that needs to run off of very little energy. That's pretty common. It kind of happens all the time. That in itself is tricky, again, because it's also both a hardware problem and a software problem. The hardware, the chips, the physical components, they need to be power efficient. You need to switch things off correctly and do things the right way. You can't have leakage in the physical world. But then you have to have the software that works correctly with this hardware and switches the right things on and off at the right times. And if you make a software change that you didn't, maybe there was a bug that did something that you didn't think about, could completely change the power consumption of the hardware. So this kind of, again, this is a kind of a tricky situation because you have those both sides. So how do you do that? Well, first off, to solve it, you go into the first step is just checking that the hardware really is low power. This is a tricky thing. It's not easy to do this, but at least it's manageable. You have tools for doing this. You can you just measure the hardware, you kind of run it as is, but you can do that usually just on one device on someone's table. And you'd end up with a plot like this. There is some power being consumed over time. You can see the spikes. You can kind of zoom in and see why is the spike here, and that's good and all. But this is for one device. Next step, if you want to really go through this, you have to go in software, and you have to be able to kind of track the power consumption over longer periods of time and over larger networks of devices. So this is a screenshot taken from the Thingsquare software, where we can track the power consumption of a specific device over time. We see those spikes every day in this graph, and we can zoom in and see what they're doing. We can check what's going on because the software is tracking the power consumption of the hardware. And if we would introduce a bug, we could see that here, because we could just flag a device that suddenly has an unusually high power consumption. And actually, in this case, this was the graph on the right there was taken from a deployment that we had in a white goods store, where sensors were scattered out over the store to check on what people were doing. And in the night, they completely wiped the power, because there were TVs, all kinds of things that would consume power, and instead of switching everything off, they just pulled the plug every night. So what happened was that the internet connection went out, the access point, everything went down, and our wireless devices were sitting there trying to connect every now and then, and that costed a bit of power. Not much, but measurably much. So that we could see, we're seeing a higher power consumption than what we should. So we had to investigate, and we could look into it. We saw, okay, so this is because we had those nightly power outs. Fine. We added a switch-off system, a power-off switch to the devices so that they would switch off automatically at a certain point in time and switch on back in the morning. And then we saw the power consumption go way down again. So being able to track this really helps us, but it adds this layer of complexity to the whole system. And in IoT, there's almost always a wireless component. It's really, there are a couple of cases where you have wired devices that might be thought of as an IoT system, but it's almost always wireless. And the problem with wireless is that it's weird. It's really quite weird. And we all sort of know this, because you're sitting in your home, your favorite place on the couch, but this place has really bad Wi-Fi reception. So you kind of need to move to the other side, and it's not as comfy, but at least you got Wi-Fi. So you're kind of, you can see this really in real life. And a way to think of this, a way to explain this is to see that wireless communication is a bit like light. You can be really close to the window, but because there is a window shade or something in between, you're still kind of in the dark. And wireless communication is similar to that, at least conceptually we can think of it as that it bounces around, there are shadows, and it's hard to see, which makes it weird, right? We see light, we don't see wireless communication. Again, there are ways to kind of address that. You can use mesh networking is one of the things that can get around the idea of, the idea of mesh networking is that devices help each other. If one device cannot reach directly to an access point, they would go through another device that might be in that other place in the couch. Not as comfy, but has a direct, better connection to the access point. So this will solve some of the issues in that. It also gives us really long range and other features, but it's really one of the main features is that it's able to solve some of the hard problems in wireless networking. We also can do things like frequency hopping. We switch channels depending on what frequencies are being currently used in the air. Again, we cannot see this, but we can measure it, and we can tune the protocol so that they are good at dealing with those frequency hoppings and channel schedules. Okay, so power consumption, wireless, those are pretty technical problems. Next up is that for almost any IoT deployment or solution or device that we do, the scale of it is kind of large. There are, in many ways. So first up is that if we are doing development for an IoT product, we're kind of in this situation where the first one or two devices are relatively easy to work with. A developer can have them on their desk. They can plug them into a computer. They can do things like single-stepping the software, just checking that every instruction is being run correctly. But when you have two devices, this gets hard, especially if they're going to talk to each other. You can't really stop them, and you can't really do that. But you have to do other things to kind of work around that. But at least it's pretty manageable. But because you have those large-scale systems and deployments, this is just the first step. Next step, you're at a kind of a desktop scale, 2 to 5 devices. You're now at the state where you cannot really see what's happening in each device. You need other ways of figuring out what's going on. We can't physically see it. Also, you start to run out of space, physically. You have your desk. You can't really manage it once you're about 5 or so. You have to go to an entire office if you're coming up to 5 or 10. And it gets even harder. And you're starting to get into those practical issues like cables all over the place or falling over them. And there are practical problems around that, not just the problems around scale and development. Okay, but say that you've done that and you're good. Next step is testing this as a kind of a large scale, starting between 10 or 100 devices. Well, that would take up like an entire floor because you need to have some kind of distance. You can't just package everything together if you want to test how things work in the more or less real setting. It's wireless and all that. You need to get the range out. So this picture is from a customer deployment in industrial lighting. So those lamps are actually quite a way up in the air. They're deployed in the actual location. That means that it's really hard to physically get to them. So if you make a mistake, some kind of change happens that would completely break it, and you need to go and pick them down. That's not a good thing. So you need to get around that and do things like over-the-air updates of the software is essential here. You can't get away from that. There's no way to physically go and update things with a USB stick or so. We have to have over the air. Plus, once you're starting to get into the range of like hundreds of devices, something with a 1% probability of happening is starting happening a lot. And this really goes even further if you're at the deployment scale. You're putting hundreds of devices, the first version of your system, you're starting to see that with things like the physical items, the physical things like soldering joints or hardware, that hardware never has a perfect yield. It's never 100%. And say that you have 5% of your hardware devices are problematic, well, you're going to start noticing that at this scale. So you have to build tools around that. So for example, this picture is taken from a deployment where those devices there in those boxes were to be deployed by our customer had hired a group of students to get those out into the actual location where they were supposed to be. So we had developed an app to help that installation go smoothly with a checklist of turn on the device, check that it's working. If it's working, take a photo. If it's not working, mark it as a failed hardware and take another one. And quite a few of those pieces of hardware ended up just being broken because of this problem. So it's once you start to get into scale, certain things become very important. Sure.
I'll ask you a question. Do you do long-term testing on this then?
Sorry?
Do you do long-term testing on your devices then? I
Yes.
mean, do you put them in place where you can have them easily accessible and then just run it for, I don't know, a month, weeks?
Yes, definitely. What we do is actually we're having test beds, which is kind of smaller versions of the actual deployment, but at a more manageable scale. So it could be like a bookshelf with 100 devices. You don't really get the same things like range, but you can see the scale, and if the code starts to break, you can notice that. And if we notice a problem in the code and we fix a bug, then we introduce back that into our regression testing framework, so that we can make sure that specific bug will never ever occur again. We kind of cover every weak point like that. So yes, definitely, we need to have those tools to deal with this. We also use simulation a lot. So we simulate devices on different levels to see that. We do simulation on very low levels, so microprocessor simulation, emulate every instruction, emulate the radio to see that things are like timing are correct, because it's timing sensitive. We do simulation of larger networks with not as precise, but with more devices, so that we can see that things don't start to break at hundreds of thousands or millions of devices. So we definitely have those tools that we work with to go around this, because it's really hard to work at this scale. Is really, really hard. This is just, you have to test it first and then go out and see that hopefully it works. Sometimes there might be things that don't work. You have to go back all the way and kind of work that through. It's really hard at this stage, and even harder if you go to the 500 or more. So you pretty much need kind of city scale. It's not just one building; it's more buildings. So this one here's the network structure from one of our customers. Just very large network. You see the mesh structure, the many different hops, and so at this stage, at this scale, it's really hard to figure out what's going on without automated tools. You have to have all those tools to do that. So, like you said, test beds, testing in smaller scales, testing up, and then keeping track of what's happened in the real world. Things like really lightweight crash logs. If something crashes, something happens, we can figure out why by just looking at that really tiny piece of information that we gather. And then again, regression testing. This is a screenshot from our internal regression testing that we do of our platform. There's a couple of those tests that we run. They tend to take some time to run because we do that large scale, so up to an hour per test. But it's really needed. We need this to be able to make sure that it works when you go out in 500 units or thousands of units. So finally, the kind of the last point in this list is that adds to the complexity of this is there's just a wide range of technical expertise needed. So this is more of an organizational level again. If you're putting together a team to build an IoT system or an IoT product, you need a pretty wide range of people. Hardware designers, embedded firmware developers, wireless communications experts. You might need someone. Things like antenna design is really important. We've seen that hardware where the antenna was faulty suddenly just didn't work when it was put out. It wasn't really faulty. I mean, it worked. It was just tuned in the wrong way. So once it was out, and this was for a deployment where the devices were pretty close to water, things started not working. It worked in the lab, but not in the real environment. So you need to have that kind of expertise. Backend developers, database people to work with the cloud deployments. Front-end developers, if you need, you probably need that web front-end, something like that, to watch the stuff from a web browser. Apps, definitely. Automation systems, integration engineers like DevOps, cloud failover, all that. Data scientists, if you want to do something with the data. And this is not even counting all the people who are in the actual problem area, who knows about the market. This is just the kind of generic technical expertise that you need. So it is pretty complex.
Yeah, and here I have another question. I mean, do you see this being commoditized?
Yes.
I mean, if you look at software development, a lot of things that 10 years ago was very high tech, or people or companies built their own solutions around. Today it's like open source. You have Kubernetes, you have Docker.
Yes, definitely becoming commoditized. And it's actually part of this, how do we deal with this? I mean, what is the way? Because this looks really bad, right, the way I presented it. It's a mess. It's complicated, it's complex, there's lots of things going on, and it's really hard, and nobody knows anything. It's really, really hard. But yes, there are ways to deal with this. And as you said, commoditization is part of this, or we could call it platforms. There are now lots of platforms that help to solve parts of this. It's hard to solve everything, because again, there are all those use cases, it's pretty complex. So you can't really solve everything at once, but you can solve parts of it. You could have a hardware module with an antenna built in. You could have a database system with a front end. And you could sort of put a lot of that together and get as much as you can into those platforms that are out there. But, so yes, there are ways to deal with this. But then actually, one of the things that we've seen is the second thing, how do you deal with this complexity, is actually to not deal so much with the complexity. But focus, and this is one of those things that should be, it's like a no-brainer, but you need to kind of say it over and over again. As a user of an IoT system, you need to focus on your problem, your business problem, for your users, your customers. Not worry too much about the tech, because the tech is moving along, it's actually pretty good at this point. But we've seen this a lot of times where it's easy to get caught up in the technology. It's easy to think that the technology is the solution, but the technology is just a means to an end. Like as any business, your job is to make sure that your customers are really, really happy. That's the thing. You need to solve those problems. And the IoT, the tech is just a way to do that. And the way to go about that is, one idea which works really well is to build prototype, build proof of concepts early, involve your customers as soon as you can, really as quickly as possible, because the way that you think of the problem is different from what they think of the problem. I'm sure that we'll see, because the talks today, I think, really covers this a lot. So I thought I'd open this up for the next speakers here. Super interested to see the rest of the day here. And the fourth point here is, don't wait. Don't wait for that one big solution, protocol, standard, because it's here today. If it solves your problem, just go for it. And maybe you can do the next version using that big solution, that big protocol, whatever it is. Maybe it's caught up to us then. Probably not, but maybe. And at least you can think of it like that. There are lots of good products out there that have been built using some pretty weak tech, the first version, and then go on to be really successful. Like the Ring doorbell. I'm not sure if you know about the Ring doorbell that was acquired by Amazon for $1 billion a couple of months back. The first version of the Ring doorbell had 1-star reviews at Amazon, but hundreds of them. So there was a need, but the tech just wasn't there. So they release version 2. That was great. So you can do that, but don't wait. Again, there's this old proverb that the best time to plant a tree was sometime in the past, hundreds of years back. The second best time is today. And I think that really captures this, that don't wait, just do it. And with that, I thank you for your attention online, wherever the camera is right now. Everyone here in this room, and you're welcome to just drop an email at adam@thingsquare.com and visit us at www.thingsquare.com.
Do you guys have any questions in the room? No?
So are there questions coming from the YouTube chat?
Not right now, but I have one question.
Sure.
I mean, you've been part of building your own, or you started up Contiki operating system.
Yeah.
Are you using it?
Yes.
Yes.
Yeah,
I just want to check.
Eating our own dog food. Yeah.
Has that evolved anything, or is it the same as it was 10 years ago?
Oh, it's very different. But I guess the basics kind of is the same. I mean, as with any software, you have a core which is kind of similar to the original ideas are kind of there, but then things have evolved over time. But it's in a way similar, in a way it's very different. But it's still kind of a part of it is in there. So
there's still a need to be very small. I mean, the software.
Yeah, the firmware that goes onto the devices, there is this thing where there is a class of devices that are super power constrained, where things are tight in every dimension, including the memory and the processing power. So even though it would be great if we could just run Linux on everything, and at one point we will probably do that, but we were sort of wanting to do that for the past 15 years, and we're not there yet, so it might be 15 more years. Even though things are it's always an evolution, but we're not quite there yet.
How do you see it with the battery or the evolution of batteries? I mean, currently, I assume you have a lifetime of what on your devices that you?
Yeah, we have years. It depends a bit on the use case, but years. I think. I mean, batteries are developed pretty quickly because of things like Teslas and large-scale batteries. I think this will probably trickle down into the tiny batteries as well. Right now, we haven't seen any. There may be some major advances happening that we just haven't seen, but we're kind of not. It's not something that happens right now, at least for us.
How do you see, I mean, when you deploy stuff, do you calculate on lifetime cycles? Like, well, you will buy this IoT from us, and then in 3 years, 5 years, I don't know, you will have to switch every device, or how does that work?
Oh, I mean, not really. We tend, I think most of our customers and us tend to think of it more as a longer term thing, mostly because the investment is pretty high often. That you're doing this, it's thousands of devices, hundreds of thousands of units. So you really want this to last for a long time. But then you have, if battery operated devices, we certainly have a life cycle of the battery. But then we plan to change the battery or recharge it. We have solar power rechargers, for example, depending on the application.
Yeah, we have one question more here. Do these devices communicate over TCP/IP, or do you do other? Yeah,
actually we do. We use IPv6 from every device, and really everything is using IP. And then we're not kind of globally routing everything, but we're definitely using the same protocol suite all the way out into the lifetime of years devices.
Yeah, if there is any more questions, please do them through the chat.
Yeah.
Yeah, we'll see. Otherwise, thank you very much, Adam,
thank you.
For coming and holding this presentation. Super interesting and very nice to meet you. I heard about you first time 10 years ago.
Hey.
Yeah.
And now we meet.
Yeah, exactly. And now we meet. Such a coincidence. And to thanks from us for coming. Like a small gift from us.
Thank you very much.
Yes.
Great.
Yes, a big applause for Adam.
Thank you.
Thanks. And now we'll take like a 10-minute break, and then Irfan is up.